All right, welcome. In this explainer, we're going to build your toolbox for understanding the physics of motion, or as physicists like to call it, kinematics.
So, let's start with something you probably use every day. Ever wonder how your GPS knows exactly when you're going to arrive? It's not magic, I promise. The answer is all about the fundamental principles we're about to get into.
So here's what we've got on tap. We're going to start with the basics, like what even is motion, and build our way up, step by step, until we can figure out the path of a thrown ball.
All right, let's jump right in. Section 1. We've got to start with the most basic building block of all. What does it actually mean for something to be in motion?
You know, it sounds super simple, right? But this one idea is what everything else rests on. At its core, motion is just an object changing its position over time. That's it. If it's in one spot now and a different spot a second later, well, it's in motion.
Okay, so now that we know what motion is, we need a way to talk about it. A language for the journey. And to do that, we need to get clear on two really important ideas that people mix up all the time.
Okay, think about this. Let's say you walk all the way around a city block and end up right back where you started. The distance you walked might be, a whole kilometer. But your displacement, that's zero. Zilch. Because displacement only cares about the straight line from start to finish. So yeah, distance is the total path your Fitbit tracked, but displacement is just how far you are from where you began.
And this is a huge deal in physics. It leads us to this idea of scalars versus vectors. See, distance is a scalar. It's just a number with a unit, like 10 kilometers. That's it. But displacement, that's a vector. It's 10 kilometers east. It has that direction component. And that's the whole ballgame right there. Scalars just tell you how much, but vectors tell you how much and which way.
All right, let's keep going. Now we're going to see how this whole scalar versus vector thing plays out when we start talking about how fast something is actually moving.
So, speed. This is the one you know. It's the number on your car's speedometer. It's a scalar, which means it just tells you how fast you're covering ground. It doesn't care one bit about which direction you're going.
Velocity, though, that's the vector version. It's speed, but with the direction attached. So 60 miles per hour is a speed, but 60 miles per hour times north, now that's a velocity. And that's the information your GPS needs to figure out where you're going and when you'll get there.
Okay, but what happens when your velocity isn't staying the same? What if you're hitting the gas or tapping the brakes? Well, that brings us to our next big concept. And the key word here is velocity. Remember, velocity includes direction. So this means acceleration isn't just about speeding up or slowing down. This is the part that trips people up. You are also accelerating anytime you just change your direction.
Right, so positive acceleration. That's the easy one. You're in your car, you press the gas pedal. Your velocity is increasing. Simple as that. You're speeding up.
And then, of course, the opposite is hitting the brakes, right? You're slowing down, your velocity is decreasing. Physicists just call this negative acceleration. You might also hear people say deceleration, same thing.
So what about zero acceleration? Well, picture this. You're on a perfectly straight highway. You've got the cruise control set. Your speed isn't changing and your direction isn't changing. That means your velocity is constant. And if your velocity is constant, your acceleration is zero.
Okay, so we've got all these concepts down. Now let's put them together into the actual toolkit, the equations that physicists and, yeah, your GPS use to actually predict motion.
Okay, here they are, the big three equations of motion. Now don't get spooked by the letters and symbols. Think of them like recipes. If you have some of the ingredients, like the initial speed or the time, you can use these formulas to figure out the missing piece, like how far something went. The first one helps you find the final velocity. The second is great for finding displacement when you know the time. And that third one? That's a lifesaver, when you need to find displacement, but you don't know the time. This is literally the math engine running inside your GPS, constantly calculating where you're going to be in the next few seconds. Another awesome way to see the story of motion is with graphs. And this table right here, this is your cheat sheet. Let's take a velocity time graph. The slope of the line, how steep it is. That tells you the acceleration. But check this out. The area under the line, that's the displacement. It's a really cool visual way to see exactly how far something has gone.
All right, it's time to put it all together. Let's take everything we've learned, our entire new toolkit, and use it on a classic real-world problem that isn't just a straight line. Yeah, let's talk about projectile motion, like throwing a ball.
Okay, So here's the secret to projectile motion. The big trick is to realize it's not one complicated problem, it's two simple problems happening at the exact same time. You just have to split the motion into two parts, horizontal and vertical. Horizontally, if we ignore air resistance, the ball is just coasting. Its velocity is constant. But vertically, oh, that's a different story. It's in a constant fight with gravity, which is always pulling it down, always accelerating it downward.
So what do? We take our trusty kinematic equations and we apply them to each direction one at a time. It's amazing what you can figure out. For example, we can use the vertical motion to calculate exactly how long the ball will be in the air. Then we take that time, plug it into our horizontal motion analysis, and boom, we can predict the exact distance it'll travel before it hits the ground. So for a projectile fired at 20 meters per second at a 30-degree angle, the math tells us it will land precisely this far away.
So, to wrap things up, I want to leave you with the little brain teaser to see if it all clicked. Here it is. A car is going around a corner. The whole time, the speedometer stays locked at a constant 30 miles per hour. So my question is the car accelerating? Think back to what we said about the real definition of velocity. If you remember that, you've got your answer.